are now at 1:15, so I will begin because we only have 40 minutes. That's why I said that this is a medium deep dive into asymmetric cryptography. Normally this talk is an hour, so hopefully we make the best use of the time that we have. My name is Eli. I am a research software advocate at a research institute based out of Oxford. I don't do maths for a living, actually. I work with epidemiologists, but I did study maths at university, and today I'm going to tell you about some of my favorite bits of that. On the agenda for today, we have talking about a brief history of cryptography, sending encrypted messages. We're going to talk about how RSA encryption works and show a worked example. We're going to talk about elliptic curve cryptography. There is a worked example in the slides for this, but we won't go through it. But if it is there, if you would like it, I can send that to you afterwards. We're going to talk about quantum computing, the new hotness that's not AI. And on that note, I'm deeply honored to have as many of you here in this slot as there are, because this talk slot here at Øredev is packed, and there's a quantum computing talk that I really wanted to go to. So thank you for being here. We will be talking a little bit about quantum computing. And lastly, to wrap up, I'll talk about what's next for the world of cryptography and what do I hope to see in the next few years. Right. So, cryptography, sending hidden messages. Humans have wanted to do this as long as we've been communicating, right? It's fun to have secrets, and sometimes it's strategically useful, right? Here's a very basic cipher. I would like to send the secret message, Øredev is great, because I'd like to keep this secret so that it doesn't get oversubscribed and we can keep it, just to us, the people who already know that Øredev is great. And what I'm doing here is I'm taking each letter and I'm shifting it by a certain amount through the Latin alphabet, right? And you can see that I've done a bit of English colonialism here, and I've said that the O with a bar through it is the same as just a normal O. I'm English, it's fine, you can hate me. And what we're doing here when we do this kind of cipher is we're essentially treating all of these letters of the alphabet as numbers. And then we're performing some mathematical operation on those numbers. And what the result is of that operation is the encrypted message. So we're taking text, we're taking information, we're turning it into numbers, and we're doing maths with it. Now, this kind of cipher, a Caesar cipher, is very simple to understand. As long as the person who is receiving your encrypted message knows the mathematical operation you performed, they can easily reverse it and get the original message back. However, this is very easy to break with letter frequency analysis. You can inspect an encrypted message and reverse engineer what was done to encrypt it. However, at one point, this was military-grade encryption. It's called a Caesar cipher because it was supposed to be used by the Roman army. We can do better than this, though. We can do something where we take our message and we turn it into numbers. And then instead of adding the same number to all of those numbers on the right-hand side, we can add different ones. We can use a second message, some kind of secret key, some kind of private key, turn that into numbers, and then add them pairwise to get an encrypted message. So here you can see you've got 15 and 19, sum to 34, and so on and so on. We then take the modulus of 26, because there's only 26 letters in the Latin alphabet, because I'm English. And then we take those numbers and we turn those back into letters. And this is much, much harder to break. In fact, if your secret key is as long as the message that you're trying to encrypt, it's impossible. It's cryptographically impossible to do so. However, in order for this to function as a cryptographic system, in order for me to recover the original message that you sent to me, I need to know your secret key. So we're back to square one. How do we get into a situation where two people both know the same secret? So this is symmetric cryptography, right? Symmetric cryptography requires both parties who are using the crypto system to already have some kind of shared secret that they can use in the mathematical operations that they're using to perform cryptography. This means that you have to have a pre-existing relationship with that person in order to have established that shared secret. For example, when you set up things like a SAML authentication relationship, when you exchange certificates and things like that, you'd need to do something similar to that beforehand in order to be able to use symmetric cryptography. How do we get ourselves into that situation in the first place? Well, that is where asymmetric cryptography comes in. It doesn't rely on two people having ever communicated before to function. Instead, it relies on complex math problems that are very expensive to compute the solutions to, at least with classical computers. And what we use asymmetric cryptography for in our actual daily lives as people who use the internet and who work in technology is during a TLS handshake, you use asymmetric cryptography to get to the point where you have some shared secret that then you can use for symmetric encryption, because symmetric encryption is much, much faster and cheaper to perform. It just requires that overhead, that setup. So it's just an implementation detail, really, but the maths is very cool. So let's get into the maths. Who here has heard of RSA encryption before? Yeah, you're in this talk. I would assume that most people have heard of it. How many of you have studied how it works on a mathematical level? Many fewer. Right, well, all of the rest of you will be able to put your hands up after seeing this talk. So RSA crypto system, it was invented in, well, it was published officially in 1977 by 3 mathematicians whose names began with R, S, and A. However, it was also independently developed by somebody called Clifford Cox at GCHQ, the British intelligence agency at the time, in 1973. And the mathematicians he worked with and the intelligence people he worked with said, well, that's neat, but I'm sure it doesn't have any practical application. And so it was just buried in the archives. And then these 3 guys independently published it in 1977. And the maths that's involved here, all asymmetric cryptography relies on certain maths being hard to perform on a classical computer. And the maths that is hard to perform that allows RSA to work is the fact that if you've got a big number that's composed of 2 primes multiplied together, and you know that big number, it's really hard to rederive the primes. It's a one-way thing. You can multiply 2 primes together very cheaply, but factoring a big number is difficult. And that difficulty is what is the difficulty of decrypting encrypted messages in RSA. If we can crack that, if we can do that efficiently, RSA falls apart. That will become relevant later. So let's take a worked example. RSA works by one party publishing a public key, and that public key can be used by somebody else to send them an encrypted message which they can then read. So what we're going to do is we're going to start with our 2 secret prime numbers, 17 and 19, obviously very large, very difficult to compute, right? But we can keep them in our heads, so that's why I've chosen these. And we're going to set up a public key. So what we need to do in order to do this, there's some certain maths that we need to perform. We need to know a certain number, which is called the Carmichael quotient, lambda n. And this has a special property where, let's say I pick some number 5, 8, whatever, any number a that does not share any factors with n, so it doesn't have any factors of 17 or 19. That's what coprime means. It means they share no factors together. If I raise that number, let's say 5, to the power of this special number that we're trying to find, it will always have a remainder of 1 when you divide it by 323. We're going to be working a lot with modulo arithmetic in these examples. So 1 mod n here in this case means that it has a remainder of 1 when you divide it by 323. And we can find this number if we know the factors of 323, which we do because they're our secret special primes. And the way that we find it is we look at the lowest common multiple of this secret special number for 17 and 19. And when those numbers are primes, the secret special number is just 1 minus that. If you take any number and let's take 17, any number raised to the power of 16 will have a remainder of 1 modulo 17. That's just a maths fact. And what we can do is we can find that this special secret number is 144. What you need to remember about this is that knowing the relationship between 144 and 323 depends on knowing the prime factorization of 323, which is not public knowledge, right? Now, we choose some smallish number that's co-prime to 323, so shares no factors, and let's say 5. Next, what we have to do is we have to find a number that relates to E. We have to find a number such that when you multiply it by E, which our E is 5, you get something that is 1 more than your secret special number, 144. And in our case, this will be 29. 5 times 29, 145. That's 1 more than 144. If our special number if 5 hadn't divided 145, 1 more than our special number, we could have kept looking at higher and higher multiples, right? Plus 1. And you will always be able to find this, just mathematically. Right. What you need to know here is that 5 is kind of random, and that D can only be derived if you know the secret special 144, if you know this, which you can only get if you know the secret special primes. So D is hard to compute if you don't know the factorization, right? And this is our public key. Sorry, that's not our public. D is our private key. Our public key is our big number, 323, and our little number E, which is 5, which we just kind of picked. It just shares no factors. It's not special other than that. And our private key is 29. So if somebody wants to send us a message, they want to send us a message. And I wrote this talk originally for NDC, which is why it's that example. Øredev was way too long to go through and work out examples for. So they want to send us some arbitrary numbers, let's say. What they do in order to send us a number, send us a message, is they raise their numbers to the power of 5, our public key E, right? And then they take the modulus of the big number. So they're using both parts of the public key. They're raising their numbers to the power of E, and then they're taking the modulus n, right? And that's what they send to us. We have received this message that is their original message raised to the power of E, mod 323. And then what we do is we raise it to the power of our private key, 29. And then we take the modulus of n again. So it's sort of exactly the same thing, but we're using our private key and they were using our public key, right? And we get back the original thing. I did actually do this in Wolfram Alpha. Don't try and raise 243 to the power of 29 by hand. You run out of paper very quickly. Why does this work? Well, it works because of that property of the secret special number 144 that we derived right back at the beginning. This has the property that whenever you raise any co-prime number to the power of that number, you get 1 mod 323, right? Now, if you raise both sides of that, if you multiply both sides of that by the original number again, you get the original thing back. Raising something to the power of 145 is an idempotent thing, modulo 323. And that's exactly what we've done. We've just split it in half by factorizing 145. So the first person sent us, the person who sent us a message, did the first part, they raised it to the power of 5. And we knew the secret special thing we needed to raise it to get back to where we started. And that private key can only be derived if you know the prime factorization of the public key, the big number that's part of the public key, which is hard to do on a classical computer. So that's how RSA works. It uses very basic sort of, I say basic, it uses very elementary, this is a form of group theory, modular arithmetic, to be able to essentially take something that's an idempotent operation, split it in half in a way that cannot be easily sort of undone, reverse engineered, send that sort of intermediary thing, that's the encrypted message, and then when we get it, we can complete the operation recovering the original message. Everyone with me? Cool. That was a very fast run through of this, right? Cool. So limitations and considerations of this. It requires large prime numbers. It requires that you keep them fairly secret, because if there's lots of publicly known very big prime numbers, people could do a sort of brute force attack on your public key. These can be expensive to find. We don't actually use sort of the biggest prime numbers that have ever been found for this, partly because they're public and also because of various other considerations, sort of complex maths considerations. If E is small enough, if your 5, the number we used there, is small enough that when you raise your message to that power, you still don't get up to the big number n. So for example, 3 to the 5 was 243, right? Somebody who was inspecting that public traffic could look at that and go, wait, 243 is a 5th power. That's 3 to the 5. I bet what they've done to get that is raise 3 to the 5. And they could inspect it and reverse engineer it, because that modulo operation that you do before sending your encrypted message is actually obscuring information, right? So if you never perform that operation because the number was still too small, you aren't doing that obscuring. So you can't just pick, the reason you would like to pick a really small number for E is because it makes it cheap for people to encrypt messages to you. They don't have to raise something to a big power, but the trade-off is that you might end up losing some security as a result. And without padding, which is just adding in extra bytes, adding in extra sort of information to obscure your original message, essentially, there are certain chosen plain text attacks that people can perform because of the way that this maths works. So, we've been talking about modular arithmetic a lot, and this is a type of group theory. Well, I'm going to teach you some group theory. Who here has studied group theory before? Only a couple. Excellent. Well, again, you'll all be able to say differently after the end of this talk. So here is some modular arithmetic. It's like a clock, but we've got rid of one number because we're working with 11 rather than 12. We like to do this with prime numbers. It gives us a lot of nice mathematical qualities. And we sort of intuitively know how this works. You add numbers and then you take the modulus of 11. You don't go off into infinity, you go round and round the circle. Now, when we do group theory, what we have is we have a bunch of objects and we have some operation that combines them. And that operation that combines them, we need to have certain properties of our group of things and our operation. And then if we have those qualities satisfied, we can say this is a group and we can start doing cool maths with it. And these are those properties. You need to have an identity element where it's a non-op to combine it with something else. In our case, we're using addition, so the identity element is 0. You add 0 to something, it doesn't change. You need to have inverses. So for everything in the group, you need to have something that you can combine it with to get back to the identity. You need to have negatives in this case. And in our case, for this number wheel, 10 and 1 are inverses, right? You add them together, you get 11, which is the same as 0. So the sort of vertical line of symmetry gives you the inverses in this case. You need associativity, which is what it's called when it doesn't matter which order you perform operations in if you're doing them with more than two things. So when you're adding things, it doesn't matter which order you add things in first. But when you're doing, for example, subtraction, it does matter. You'd have to have brackets there to tell you what the correct thing was. But in groups, you never do. And you have to have something called closure, which is that if I combine two operations, if I combine two elements, I always get back to something that is also part of this set. If you have all 4 of those qualities, you are working in a group, and you can say lots of nice things about the way that that group behaves. So one thing we can do with a group is, we've said we've got addition here as our operation. What if I wanted to add 4 to itself 13 times? Well, we have shorthand for that. We have notation for that. We call it multiplication. And it works, in this case, it works very similarly to what we expect, but there's a bit of subtlety here that I want to point out. The 13 that we're multiplying by here is not actually the same as, like, it isn't in the number wheel, right? It's just saying we're combining 4 with itself 13 times. And because the combination operation that we're using here is the addition that we're all familiar with, this does actually work how we expect. We do 4 times 11 plus 8. So, you know, you've got 13 is 11 plus 2, so you do that. And you end up with 8. And if you did 52 mod 11, you would also get 8. So this does work out in the way that we expect. But what I want to point out is that, let's say we had, instead of numbers, these symbols, and they have the same relationship as the numbers do to each other. But suddenly, it's not at all clear that star times 13 should equal club symbol. But it's not about, the 13 is not sort of a number that's part of this number wheel. It's shorthand for 13 lots of a combination operation. Does that make sense? Because that's the subtlety that's going to let us understand elliptic curves. Another example of things where you find groups is things like rotations of objects. Groups are everywhere once you start looking for them, and they're one of my favorite parts of maths. So this is the formal definition of a group. If anyone wants to take a photo of this, but the slides are also, I will make available to you all. So elliptic curve cryptography, and we have just over halfway to go. Fantastic. This is an elliptic curve. What it is it's an equation, a graph, right? And it takes the form y squared is x cubed plus ax plus b. And instead of working over like the normal numbers or the real numbers, we're working in modulo arithmetic. We're working in whole numbers modulo some prime number. That's what that ZP means. It means integers. And we're only considering the ones between 0 and some prime. And when we get bigger than that, we take the modulus. So in fact, we don't have a whole line of solutions. We have blobs. We have distinct points on this curve that solve this equation, right? Because there are only so many real points in this thing. We're looking at a grid more so because we're working with integers only. So the set of solutions to this equation in ZP is the points on an elliptic curve, right? And we then define a combination operation on all of these points. So suddenly, we've got a set of things and a way of combining them, right? We say that there's a point at infinity which solves this equation, because infinity squared is equal to infinity cubed plus a infinity plus b, right? Because it's all infinity. So we say infinity solves this equation, and we say that that is our origin point. We say that not our origin point. We say that's the point at infinity. We say that that is our identity of the group, right? That's our 0. And we have this combination operation where we say, well, let's draw a line and we'll see where it intersects with the curve again, and we'll say that these have some kind of relationship. And I'm going to skim through these next bits because what you really need to understand is that this, like drawing a line and saying that these three things have this relationship, gives us a group action on the elliptic curve that we can use to say that these blobs and that combination operation are a group. So if we've got A and B, we draw a line through them and we get some other point, C. We say that all of these three things sum to the point at infinity. What does that mean? Well, it means that C is the point at infinity minus whatever A plus B is. Therefore, A plus B is minus C. So this is our combination operation here. What is minus C? Well, if we look at 2 points that are inverses, that are on top of each other, we draw the line through them. It never intersects the curve again. We say that it intersects at infinity, because obviously this line goes off to infinity, right? Which means that A is minus B. So we have inverses for every point on the curve. We have an identity element, we have inverses, we have associativity, just as a thing that you can just prove, and we have closure. So we can say that we know that when you do this operation, you will always land on some other solution in the curve. Right, here's a real one that I worked out by hand. This is the one that I used for the worked example that is in the end of the slides. It took me a couple of goes to find a curve that would give me certain nice properties that you want when you're doing encryption with elliptic curves. So we're working modulo 11 because I like it. And we can see that we have actually 11 points, 11 blobs, 11 solutions. And you can check that these x and y coordinates do satisfy the equation here if you want. When you're doing encryption with an elliptic curve and you're working modulo some prime, or you can also use powers of 2, but I'm not going to cover that because it's really complicated. You want to have as many points on the curve that actually exist as possible. You want to have the maximum number of solutions, which is that prime number. And what we can do is we can look at this and we can say, okay, if I was going to start using this for elliptic curve cryptography, what I would do is I would define the curve parameters, or I derive the curve parameters. This is your public key when you're doing elliptic curve cryptography. It's like the 323 and 5. And we get these from the curve equation and the field that we're working over, the Z11. So 11 in our case. A and B, those are the things that define the curve. G is like some special point, one of those blobs we choose and we say, this is my favorite point, I love this one the most. This is usually the same thing as P here, 11. You want it to be the same thing. And you want this generally to be 1. These all have complex math stuff going on that I will happily talk more about after this. Yeah. So if I say I've got all these curve parameters, in our case it's 11, 1 and 5, 0, 4 we've chosen to be our special point that we love the most, and 11 and 1. And the way that you combine points, this is just from the Wikipedia, you've got these nice little equations that you can use if you've got the coordinate points to go from one point to another, and like if you add a point to itself or if you add 2 points together. And using this, what I did was I said, okay, I've got my special point. If I add this point to itself multiple times, this is what I get. You cycle through all of the points on that graph, all of those blobs. You end up with a number wheel, just like the clock face missing a one number, right? You end up going through, okay, 1 times this point is that one, and then again that one, and then again that one. And this means we can do a lot of the same maths that we did with RSA, right? It's not as simple as that, but there's an analogy here, right? It's relying on very similar maths. And something that I want to point out is that you've got inverses. 4 times our special point is the inverse of 7 times our special point, because you can see those are the ones that would be reflected in the x-axis. And 4 and 7 is 11, so we have that same relationship of it's essentially modulo arithmetic addition. So we have that same group structure over this elliptic curve. And that's kind of the thing that I wanted to get across, is that they're very similar mathematical systems, right? And we can use elliptic curves to do encryption in similar ways. But there are key differences, and there are reasons that elliptic curve cryptography has superseded RSA as the sort of bread and butter of asymmetric cryptography in the last few years, although that's now changing, as I will talk about in a minute. You have a smaller key size for the same security properties. Mathematically, it's harder to derive. If you had the same key size, it would be much harder to break elliptic curve cryptography than RSA. This is nice because it means we can send less data when we're doing cryptography, when we're doing encryption. Smaller payload size, again, the same benefits. We want to be sending less data. Sending data is expensive, so we want to minimize that. And faster computation as well. So basically, it's better than RSA. Fantastic, great. And this is why it's been chosen rather than over an RSA in the last few years as the go-to method for doing asymmetric cryptography. Brilliant, fantastic. We are done with 15 minutes to spare, right? Everything's great? Not so much. We built quantum computers. And in fact, even before we built quantum computers, a guy called Shaw came up with some algorithms in 1944, so over 30 years ago now, that are going to cause us some problems. So I said earlier that asymmetric encryption relies on hard maths problems. RSA relies on something called the integer factorization problem, which is that if you have a big number that's composed of 2 primes, it's really hard to find those 2 primes just given the big number. We also have hard maths problems like the discrete logarithm problem, which is about a finite field is, it's like a group, but you can also do multiplication and division. And numbers modulo a prime number have this property. So like your number wheel, you can also like divide and multiply, and you always get something that's back in the group. Yeah, field theory, very cool. If you want to raise things to a power within that group, it's really hard to undo that. And that's, that's another hard maths problem. And the elliptic curve discrete logarithm problem, which is basically the same thing, but stated in the terminology of elliptic curves. So G, our favorite special point that we love the most, generates a subgroup, which means when you add it to itself, you get a subgroup. In our case, that subgroup was also the entire group. It's really hard to undo that multiplication operation, right? These are the hard math problems that power asymmetric cryptography. And Shaw wrote an algorithm, or wrote actually several algorithms for quantum computers before they even existed. He said, I think this would work. And he solved the integer factorization problem. What he did was he said, here's an algorithm that will take any given number n, for example, 323, and any number between a and n, let's say 11, like a random number, we can find the smallest number that when you raise 11 to that number, you get 1, you get a remainder of 1, 323. In polynomial time. This cannot be done on a classical computer. This is a quantum computer thing. So, worked example of Shaw's order-finding algorithm breaking RSA. Let n equals 323, and we're going to choose a equals 11. There's a chance that the number you randomly choose won't work, about 50%. When I was doing this worked example, if that had happened, I would just have to go back and choose a different number a. Fortunately, it worked first time. Shaw's algorithm gives us, in polynomial time, that 11 to the 48 has a remainder of 1 mod 323. And it's the smallest number for which that is true. 48, there's no smaller number, right? And I sat and typed out in Wolfram Alpha all of the powers of 11 mod 323 until I got there. So much slower than a quantum computer in theory would be, but I don't have one of those. Right, what this means is that 11 to the 48 minus 1 is 0 mod 323. We can do the difference of 2 squares and halve that power. And what that means is 323 has to divide into that product. Either both the factors of 323 go into one of those 2 things, or they're split across the 2 things, and we can use that to separate out the factors of 323. We know that one of those brackets can't be true. It can't be that 323 divides it. Both factors of 323 divide it, because 24 is smaller than 48, and Shaw's algorithm told us that 48 was the smallest number for which that was true for 11. So with about, again, I think it's about 50% chance, you will find that the factors of 323 are split across those 2 bracketed terms. And what you can do is you can say, okay, if that's true, I can evaluate 11 to the 24 plus 1, which is cheap to do, and I can take the greatest common divisor of those 2 things, our number n, and 11 to the 24 plus 1. And if we find that the greatest common divisor is not 323, it must be one of the factors of 323. And this is a fairly reliable way of factorizing big numbers multiplied by 2 primes in polynomial time, which is not currently possible on classical computers. And as we know, finding the factorization of that big number allows us to recompute, for example, the private key of a crypto system based on that, which means that we can't use RSA anymore. Terrible, right? Like, this is bad. But at least we've got elliptic curves, right? Elliptic curves, smaller payloads, faster computation, everything's fine, right? No, he wrote algorithms that break those 2. So what are we going to do? And this has been something that we have known about for, again, 30 years. So cryptographers have been known about this. They've been working on this. All is not lost. These are not the only hard maths problems in the world. They just happen to all be broken by by Shor's algorithms. There are other hard math problems out there that, so far as we know, they're not vulnerable to any known quantum attacks. So what if we tried to build crypto systems based on those hard maths problems? And that's what people have been doing. This is post-quantum cryptography. So there's something called the isogeny finding problem. Given two elliptic curves, which we now know and love and understand what elliptic curves are, between which we know there exists an isogeny, which is a fancy maths way of saying these two things are kind of the same when you look at them from this angle. Find the mapping that describes it. This is a hard maths problem that we don't know. We don't know any quantum attacks that can solve it, right? And people have tried to use this to define crypto systems. There's something called psych and something called seed. These are considered insecure or side. And there was something called seaside, which was called that because the mathematicians that were developing it were like by the ocean when they made it, and so they called it seaside. But it's also called the, I'm trying to remember what it's called, the commutative supersingular isogeny Diffie-Hellman. That's what it stands for, which try saying that 3 times fast with a mouthful of peas. However, this is a paper about that, and unfortunately, the security parameters only seem to provide around half of the expected security as they should do. So this did not take off and become the new thing, the new hotness that we're all using for asymmetric cryptography. But I like it because it's called seaside. So seaside also considered insecure. So isogeny finding problem didn't give us new crypto systems. However, there are more math problems. The learning with errors problem is, this is like, I know some hard maths, this is like magic, this is witchcraft. You basically introduce statistical noise to your encodings and then do some kind of magic to like factor it back out at the other end. Don't understand it. But what it did do is people managed to define crypto systems called crystals Kyber, key encapsulation, and crystals dilithium for signatures, 2 of the things that we currently use elliptic curves for. And these have now been accepted by NIST and are in usage. So one of the things that people are doing at the moment is we're sort of using both elliptic curve cryptography and these new post-quantum ones at the same time to kind of hedge our bets. So for key encapsulation, or for signatures rather, you've got a message and you sign it with ECDSA, and then you take a post-quantum signature over the whole thing. So that even if, for example, the post-quantum one, somebody discovers an attack tomorrow that can break it, you've still got the security of ECDSA for now. And vice versa, if somebody manages to solve, if we have quantum computers that are going to be able to decrypt ECDSA, elliptic curve cryptography, you've got the post-quantum one there for security as well. Similarly with key exchange, they're doing sort of half and half, 32 bits generated by each. And it's worth saying we don't have quantum computers now that can break current elliptic curve cryptography. But we might in the future, and it's cheap to store data. So the thing that people are worried about here is something called the harvest now, decrypt later paradigm, where people are snooping on your traffic, saving it to big old hard drives, and in 15, 20 years, if it's still relevant and sensitive data, decrypting it then. And if you are, for example, a nation-state actor, that's a very real threat. So that's why these kind of things are becoming pressing now. But we do actually have the maths to protect ourselves from it. In Chrome, you can now enable this. I think Firefox might have it as well. These things are rolling out, and you can use those in your day-to-day as an end user, as somebody who browses the internet, but also as developers when you're designing systems and you're designing like clients that work over the internet and want to use encryption. There's something called Open Quantum Safe. This is a C library where people are implementing all of these sort of there's other quantum, post-quantum algorithms now for encryption, and people are working on them and having this open source thing, and it's C, so you can basically wrap it and put it wherever you like. There we go. Yeah, this was in May of this year. Post-quantum cryptography is coming to operating systems. There's a lot of primitives now in various programming languages. For example, I think .NET C# is bringing out, I think maybe already has brought out post-quantum cryptography primitives that you can just drop into your code, making it very low friction to just immediately upgrade the security of your systems, essentially. So with almost at time, what I hope to see going forward is I would like to see more diverse quantum resilient crypto systems. So the whole thing with the hard maths problems, we've got those 3 hard maths problems that Shor's algorithms broke. So far, we have, I think we're now at a couple of different hard maths problems that are powering the next generation of quantum resilient crypto systems. What if somebody else designs some quantum algorithms that break those, right? If we have more and more hard maths problems powering these, we have a more diverse set of quantum resistant algorithms, then we protect ourselves against the possibility of new quantum attacks being developed that can break those hard maths problems. So the more of those we have, the safer we are, the more fallbacks we have. So I'm sure cryptographers are working on this because it seems like a very obvious sort of concern. But yeah, lots of work for cryptographers still out there here in 2025. I would like to see quantum resilient hardware tokens. I love hardware tokens. I love the technology behind them. They use asymmetric cryptography to do some very cool things. And I have a whole talk about them. And I would love to see them with quantum resilient algorithms on them. I think some of these are being developed. I don't think they're available for commercial purchase, but that would be super cool. And given that browsers are now more and more able to handle these quantum resilient algorithms, you could just drop that state into, you could be doing your like hardware token authentication with quantum resilient algorithms if those existed, or if those tokens existed. So I think that'll be really cool. And wider accessibility and rollout of these algorithms. Like, as I said, these are coming to programming languages. These are in your browsers already. Having people know about them and using them is just going to sort of generally raise the level of the security of our internet traffic as a sort of just in general. And that's good, right? How many people came in here worried that quantum computers were going to break encryption entirely? Okay, a couple. So I've done this talk before and I've had almost the whole room raise their hands. But hopefully those of you who did raise your hands are a little bit more reassured now. Yeah, we have been known about these for 30 years and the maths is there, but there could be more maths and that would be great. So yeah, wrapping up, we've talked all the way from a Caesar cipher, all the way through some group theory. I've taught you what groups are. You are now mathematicians. Go forth and do maths. We've talked about quantum computing. You've seen a worked example of Shor's algorithm breaking RSA, even if it was a very fast-paced one. And we've talked about what's next in the world of cryptography, or a very small part of it. So thank you so much for your time and attention. I think we might have a couple of moments for questions. Please do give me feedback and come and grab me afterwards for the slides and for more chat. Thank you. I'm not going to pressure anyone to ask questions. Oh, we do have questions. Hello.
More of a history question, maybe.
Mm-hmm.
Did you say that Shor's algorithm was coined around the 40s?
No, Shor's algorithm was 1994.
1994?
Yeah, 1994. Yes. Same year as me. Yeah.
No, but I was wondering when sort of the post-quantum cryptography issue came up on sort of in the cryptography communities on top of mind. So.
Yeah. So the question is, when did the post-quantum cryptography issue come up and sort of be top of mind in the cryptography community? I don't actually know definitively, but I would have to assume that around the same time, because. Well, I actually don't know, because I don't know about when elliptic curve cryptography was developed and superseded RSA actually in terms of timeline. I just know the maths of it. Yeah, I know that it's been a focus of sort of industry development. People have been thinking, oh, we need this for industry since, I want to say, about 2010, but it could easily have been before that. And it's one of the things where the study of pure maths, often people go into pure maths because it makes their brain go brrr, right? Not because it's necessarily going to be very lucrative or have industry impacts. But then we find out that there is actually industry applications of these things. So it's very possible that people were working on the maths that ended up going into these things without the intent that would happen, just because it was fascinating to them and they wanted to develop it. Mathematicians are a weird breed, and yeah. But thank you very much for the question. Yes. Any other questions? If everyone wants to go and get coffee, I will not be offended. Go and beat the coffee rush. Oh, one over there. Yes. The slides. So the slides are in my GitHub. I will post these specific versions of the slides because I did make some updates. I will post this on my GitHub, and I will. What's the best way to get them to people? Is there there's not a Slack or anything or a Discord for this, is there? I don't know. Yeah, I'll put them on Blue Sky. Yeah, that works fine. I will do that. immediately after this. And yeah, at the end of this, hang on. So there's all my sources and stuff. And oh, did I not keep the? I'll make sure that the worked example of elliptic curve cryptography is in there as well for anyone who wants it. It's very dense. It's not great for a live talk. But yes, I will definitely make the slides available to you all because I'm aware that we whipped through that pretty fast. So, any more, or is it coffee time? All right, well, thank you so much for your time and attention. Have a fantastic time at Øredev, and thank you again for coming to this talk when there were so many good ones on offer in this slot.